Okay, chapter 9. So, chapter 9 is triangle similarity. Like chapter 4 was triangle congruency. Uh, those are triangles that are exact same triangle. These are triangles that are the same shape but different sizes, right? And that's kind of what we have done in the last two chapters with the dilations. Those are just creating two similar triangles, right? They were the exact same shape. It was just one was larger or smaller depending on your scale factor. Or in the trigonometry, you had those ratios between the sides were the same, right? Like the sine is always the same sine. If we kept the angle the same, our ratio stayed the same. So it was the same triangle shape, but different sizes. And likewise here, we're just going to add a name to this with triangles, with like naming the kinds of similarities. And unlike triangle congruency, where there were 6 or 7, I believe, here we only have 3: side, angle, side, 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 and angle, angle. Right? So, and when doing this, we want to look at sides and prove that the sides are proportional and the angles are congruent. Again, just like in the trigonometry. So starting here with side, 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 you will have, again, 3 proportional sides. And then that would look something like, if we have a triangle here and a triangle here, we'll call this X, Y, Z. Call this 1/2 X, 1/2 Y, 1/2 Z, like that. Because these are all 1/2, it's they're going to be proportional because that 1/2 will cancel out when dividing. Next, side, angle, side. So we have, let me just extend these down. Side, angle, side, angle, side. And in side, angle, side, you're going to prove that 2 sides are proportional and that one angle is congruent. Or I put the number 1 ONE. One angle is congruent. Like that. And then that would be something like this. If we have 2 right triangles like that, and we have something like X, Y, 2X, 2Y, something like that. Where again, these 2's are going to cancel out, so it's proportional to this. And then, because of the right angle congruency theorem, these are always going to be congruent, the 90-degree angle. And then finally, you have angle, angle. And I'm sure, as you guessed already, this is when you can prove that 2 angles are congruent. Like that. And then this, again, would look something coming up with an example here. This would be something like that, where we can prove that these two angles are congruent. And then these are your three kinds of triangle congruency. I'd write this down. Study this, right? I'll give you a second, pause the video, write that down. Uh-oh, that came out of the wall. All right. And then we'll get into a couple examples. And I mean, this is just like the triangle congruency. You're just trying to prove something else here. Yep, there it went. Sorry, let me fix this. Alright, there we go. That marker holder thing came out of the wall. Okay, let me give you two triangles here. Alright, we'll have one triangle like this, and one triangle like that. And then we'll say, what are we given? Well, first let me label these. That might that might help a little bit. We'll call this TFU. And then this up here is CDE. CDE. And then I'll draw our two column proof up here with our statement and reason. Again, you're using this a lot. And we are given that TFU is congruent. So angle TFU is congruent to angle DCE. Like that. So I kind of ran out of space there. And what that would look like is angle TFU, so this right here, is congruent to angle CDE, right there. So those two angles are congruent. We're also told here that this is 9 units and this is 10 units. And this is 27 units and this is 30 units. And I'll write given here. Like that. Now from there, we can check to see if these are proportional. Obviously, you look at that and know it's multiplied by 3. 9 times 3 is 27. 10 times 3 is 30. But we have to write it out and prove it on our two-column proof. So what we can say here is that EC over DC, right? So this over this, EC over DC is congruent to, or not congruent to, equal to, because we're using their lengths, or we're using the number associated with them rather than their lengths. So that is equal to, and again, because we're not using the actual lines, but rather the length of those lines, we don't put the line over top of it either, is congruent to FT and TU. FT and TU, like that. So again, all this is saying is that if we take these things here, we say, well, EC, that's 9, right? So we would do 9 over, and then it says DC. DC is 10 equals, then FT is this right here, 27 over TU is 30. And like this, you can look at that, well, this goes down to 0.9. And then we can simplify this. We divide by 3. 3 goes into both of them. That goes to 10 or 9/10. And then that also goes down to 0.9 like that. So we know that they're equal to each other, right? So we can write here 0.9 equals 0.9 like that. And then from there we have all the information we need to say that this is side angle side similarity, right? We can say that triangle CDE is similar to, and the similar to is unlike the congruency where it's an equal sign and then a squiggle over top. Similarity is just the squiggle, right? So is congruent to triangle TUV. 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 Sorry, that should be TFU. FU. Like that. And this is because of our side angle side similarity. Like that. And that would be one example. Next, let me erase this. Like that. Next one, we have a diagram where triangles are on the same plane again. Okay, it's going to look like this. Like that. We are given, if I write our, well, first let me label this. Shoot. I put D for both of these on here. I don't know, A, C, E. We'll just call this B up here. A, B, C. This is D, E. Okay, we're told that A, E, D is congruent. A, huh? Okay. I'm just going to come up with a new one. We'll use the same diagram. I'm just going to ignore the book here. So I'll say like this, where we're doing angle, we'll say that A, B, C, D, E, like that. We'll keep that. And we'll come here. I'll draw our two table, proof, statement, and reason. And you'll be given that, I don't know if we say, let's say AB is parallel to ED. And I think that should be enough. So if I write that out here in our diagram, we can say that is parallel to that. And then from there, if we go all the way back to chapter 3, 6 chapters ago, that would be, the parallel lines cut by a transversal. If we just rotate this, we could say AB or AD are these parallel or the transversal here, and then we could just go with, first, obviously we can say that these vertical angles are going to be congruent, like that. Is number one, super easy. So we can say that angle ABC is congruent to angle ECD. because vertical. Just like that. Next, we could go, again with this parallel line cut by a transversal here, we could have alternate interior angles with CED and EDA, right? So we can say that this angle here is congruent to this angle. And if that doesn't make sense, let me rotate this a little bit and clean everything up. If we say here, like this, and I'm going to extend these sides, we say this is AB, and this is ED, and then this here would be I'm sorry. Then we would have a line that goes like this, that's EB, but let's make this extend a little bit, and make these extend a little bit, and you can see here how we get these alternate exterior, or these alternate interior angles. That makes a bit more sense. Again, if you can see that up here, if we just rotate this a bit, you get those two parallel lines cut by the transversal. But now we have two angles that we prove are congruent, and that's going to be our angle-angle congruency, and we can say that triangle ABC is congruent to triangle EDC because of angle-angle congruency, like that. Let me check something real quick. Okay, yeah. I just wanted to make sure you could see this. All right. I didn't know where the camera cut off because I don't have it as far left as I usually do. Well, my left, your right. When I stand like this. Okay. Next example. Hopefully I don't screw up this book here. We're going to have two triangles like this. Here. Triangle. Triangle. And we have ABC. Like that. And DEF. Like that. We are given some lengths here. We're told that this is 84. We're told this is 70, and that this is 42. And then down here we're told 25, 15, and 30, like that. And now let me come up here. Actually, let me add a line here separating these so it's a bit easier to see the divided triangles, like that. And then our statement reason, or two-column proof. Reason, let me extend this out a bit. Okay, statement reason like that. And here, if you want to try this on your own, this is a pretty simple one. Okay, so first, if we look at these ratios here, again, if we take, well, first let's identify the smallest side on each triangle. Here, this is 42. Here, it's 25, right? And then the middle would be, the 70 and 15, and then the largest is 84 and 30. So if we take, the ratio, if we want to test the ratio between them of AC and DE, right, our two smallest sides, if we put AC over DE, you get, if you want to pull out your calculator, you get 2.8, right? And then what if we try two other sides. What if we try the middle sides? If we put, BC over DF, right? If you put that in the calculator, it'll also tell you 2.8. And if you put 80 BA over FE, you're also going to get 2.8. So we know that the ratio between all these sides are going to be the same, and we can write that up here again, right? AC over DE equals 70, which was BC, over DF equals BA over EF. Like that. And we can write our reason is 2.8 equals 2.8 equals 2.8, like that. Right? Because all those lengths are equal to 2.8. And then from there, we already have our three sides that we know are proportional, right? So we can already write that these triangles, triangle ABC, ABC, what's that? We go AB, so that's the long side. That would be EFD is congruent to triangle EFD, like that. And we can say this is because of side, side, side. And that's it for this triangle. Right? You're given enough information at the very beginning. Oh, come on. This thing fell again. I have to get something that holds it. Thumbtacks don't hold it. Staples don't hold it. Just doesn't want to stay pinned to the wall. It was made to be magnetic. This board isn't magnetic. It's... Okay, I'm just going to set that over there for now. I'll clean that up later. Do we have another example after that? Or are we off to the dreaded chapter 10? Yeah. Okay. That's it for triangle similarity. If you want more examples on that, there's plenty of examples online. Next is chapter 10. Chapter 10 will take over an hour, honestly. It took me a couple days to write, but it's fun. That's chapter 10, but it's all circles, chords. It's very specific stuff that'll help you solve very specific problems. It's about, chords, diameters, secant line, tangent line, all that kind of stuff. So next is chapter 10.